This is my lab 4 report. So the purpose of this lab is to predict circuit behavior of circuits with resistors connected in series and parallel, and then also examine the behavior of resistors and capacitors. So the important physics concepts: Ohm's law, which is change in potential difference is equal to current times resistance. Then the loop rule, which says that in a loop the potential difference is zero, net potential difference is zero. And then the node rule, the current flowing into each node is equal to the current flowing out. The model is the online circuit builder in PHYS, which is the ideal model. And then the assumptions, we assume the resistance of the wire and ammeter can be ignored, or in other words, there's zero. So for the series circuit, the prediction I made was that the current in ammeter 1 would be equal to the current in ammeter 2, and you can see that's the case. They're both equal to 0.02 amps, which I calculated here. And when connected backwards, that just flipped, it's negative 0.02 amps. So when you replace the ammeter with a voltmeter, the voltage is 3 volts because you have two 1.5 volt batteries here. Current is 0 because the circuit is open. So continuing on, calculating the potential difference at each of these points, so B minus A, C minus B, so on. We did that with the circuit builder, and this is what I got. B minus A is 3 volts, and then all these here, D minus C is negative 0.96, F minus C is negative 0.204. So if you add them all up, you get net potential difference as 0, which is expected. Also, the current is the same because even though the circuit is changed by adding the voltmeters have very high resistance, so no current passes through them. And then you see here with the graph, I basically just graphed the potential difference at each of these locations here. And so for 2.10, the ammeter reader stays the same at 0.02 amps. When you add a ammeter in parallel, the current increases to 0.06. Just because current is equal to voltage divided by resistance, and resistance decreases when you add resistors in parallel, when you connect in parallel, and so therefore the current is going to increase. Now for these here, the 47 ohm resistance is 48 ohms when calculated here, and then for the 100 ohm resistor it's 102 ohms. So it's slightly different because the resistance of the wire is taken into account a little bit with these calculations. But then for the wire and ammeter, calculation shows that it's 0 ohms. So with the RC circuits, with the 10 ohm bulb connected in series, the observation was that the bulb is lit very brightly at first and then loses brightness steadily over time. The capacitor is charging, and then when it's disconnected with the battery, the capacitor is discharging, and the same thing happens with the light. And so the current starts off very high and then decreases to 0. Then time to discharge with a 10 ohm bulb, I calculated it at approximately 8 seconds, and with a 20 ohm bulb, it's about 16 seconds. And so then we did with the 30 ohm bulb, we had to calculate the time constant RC experimentally, and then also calculate it by just doing resistance time capacitance. And so when you calculate it, it's 6 seconds. With the experimental value, I got approximately 5.98 seconds. As you can see here with this graph and then table here. So then some sources of error. For calculating the data here. It took a little bit of time discrepancy to pause the stopwatch and then to start the capacitor discharge. That's human error there that could have altered that and caused a little difference there. So what if you're using an actual ammeter instead of a simulated ammeter? If you were using an actual ammeter, the current value used would have been slightly different, since the resistance of the ammeter is not exactly 0. And then what if we use a real battery to charge a real capacitor? The capacitor would have taken some time to charge instead of charging immediately, which is what happens in the ideal scenario. So thank you so much.